Dr. Animesh Chakravarthy is a professor in Department of Mechanical and Aerospace Engineering at University of Texas Arlington. He has expertise in the areas of guidance and control of flight vehicles and is the Director of Guidance and Control of Autonomous Systems Laboratory. He received his Ph.D. in Aeronautics and Astronautics from MIT in 2007. After his Ph.D., he was a research scientist at the University of Florida, where he worked in collaboration with researchers at AFRL, Eglin Air Force Base. He was then a faculty at Wichita State University during 2011 to 2018, before moving to UT Arlington in fall 2018. Dr. Chakravarthy is a recipient of an NSF CAREER Award and was a summer faculty fellow at AFRL Eglin in 2014. In 2018, he received a Rising Star Award from the University of Texas System. In 2020, he was elected as Associate Fellow of the AIAA. His research has been funded by NSF, NASA, AFRL, ARO, and FAA. Unfortunately, Dr. Animesh could not join us here, and we are thankful for sending a pre-recorded version of his presentation.
Hello, everyone. My name is Animesh Chakravarthy, and I'm a faculty at University of Texas at Arlington. And the title of my talk here is Velocity Cones and Their Applications. The outline of the presentation is as follows. I'll first talk about collision between dynamic point objects moving on a plane, and then use that to demonstrate collision cones between dynamic objects on a plane, three-dimensional space and n-dimensional spaces, and finally talk about some of the applications of these collision and velocity cones in different scenarios. Let us consider 2 point objects A and B moving on a plane as shown in the figure on the left. Here VA and VB are the respective velocity vectors. Let us refer to the line joining their instantaneous positions as the LOS. Then at a given instant, the length of the LOS is r of t and the angular orientation of the LOS is theta of t. So as A and B move, the LOS may shrink or expand in length as well as rotate on the plane. Now if A and B are on a collision course, then their paths form a triangle referred to as a collision triangle shown in the figure on the right. And the condition for A and B to be on a collision triangle is that the loss be non-rotating and shrinking in length. This is both a necessary and sufficient condition for collision. Now we can decompose the relative velocity of B with respect to A into 2 components, V theta and VR as shown, where VR is a component acting along the line of sight and V theta is a component acting perpendicular to the line of sight. Then the necessary and sufficient condition for A and B to lie on a collision triangle is V theta equal to 0, VR less than 0 as shown in the boxed equation on the right. Now imagine that B is a circle as shown, and assuming again that the speeds of A and B to be constant, there can be multiple heading directions of A that will cause it to intercept B. We call this as the collision cone. Now, how do we calculate this collision cone? We realize that every ray emanating from A and passing through B will have distinct V theta VR values. Assume that A intercepts B at some point C as shown by the red line on the figure. Then from the results on the previous slide, we know that the points A and C will form the base of a collision triangle if V theta of AC equal to 0 and VR of AC is less than 0. Now, how do we determine if there exists such a point C? We can do so by realizing that as we sweep from the top of the circle to the bottom of the circle, V theta and VR both vary continuously with theta. And for there to exist, for V theta of AC equal to 0 to exist, the condition that V theta AB1 times V theta AB2 should be less than or equal to 0 as shown in the first equation on this slide. Now using that basic condition, we can do a bit of processing and finally arrive at the bottom equation, which represents a collision condition, and the set of heading angles of A that satisfy this bottom equation refer to the are referred to as a collision cone. Now assume that B is an arbitrarily shaped object as shown. B may be convex or non-convex. Then we can essentially use a set of similar arguments that we did in the previous slide when B was a circle. And that is to say that if we draw two lines from A that are tangent to B, as shown in this figure, then B theta varies continuously as we sweep from the top ray AB1 to the bottom ray AB2. Therefore, there will exist a ray AC with V theta of AC equal to 0, if and only if V theta of AB1 times V theta of AB2 is less than or equal to 0. Now, with some additional processing, we can obtain the collision condition between A and B as satisfaction of the inequality shown as the bottom equation on the slide, and then the set of heading angles that satisfy this equation are referred to as a collision cone. Now, in this bottom equation, we note that there is a parameter psi, which represents in some sense the angular width of the object as seen from the perspective of A. And V theta B and VRB are the relative velocity components of the angular bisector of the sector B1AB2. Okay, and in this figure, psi, the engagement geometry is such that psi is less than 180 degrees. There can be scenarios when psi is greater than 180 degrees, and that requires some additional analysis. Now consider the situation when both A and B are arbitrary objects. For A to be on a collision course with B, there should exist some ray C1, C2, where C1 is a point on A and C2 is a point on B, which satisfies V theta C1, C2 less than, which satisfies V theta C1, C2 equal to 0 and VR C1, C2 less than 0. Okay, the line C1, C2 is shown in the figure on the left. Now we can draw two tangents Q1, Q2 and R1, R2, which are actually separating hyperplanes. And using some similar continuity arguments as before, we can see that in order for there to exist a ray with V theta C1, C2 equal to 0, we need V theta of Q1, Q2 times V theta of R1, R2 should be less than or equal to 0, which is the first red equation shown in the slide. Then with some additional processing, we can arrive at the collision condition, which is the bottom equation shown on the slide. Note that this equation is identical to the one shown in the previous slide. The definition of psi is as shown in the figure on the left. Now in the figure on the left, the engagement geometry is such that psi is less than 180 degrees. There can be scenarios when psi is greater than 180 degrees, and that is shown in the figure on the right. And this case is handled with some additional analysis. Details of that are presented in the paper referred to at the bottom. So in the previous slides, we considered the situation when the objects A and B are rigid objects. There can also be scenarios where we have deforming, shape-changing objects. Examples of such objects can include snake robots or a vehicle swarm that is moving in a non-rigid formation like a flock. And in this case, the boundary of the vehicle swarm can be viewed as a deforming object as the vehicles in the swarm come closer or spread apart. Now in this figure, A is an arbitrarily shaped object and B is another arbitrarily shaped object which is also deforming. The boundary of B is represented as B of S, where S is a curvilinear coordinate. Some points on the B of S, which are C1, C2, etc., are shown, and they all have distinct velocities. Assuming each of these velocities to be piecewise constant in time, we can construct collision cones for such objects. I'll not go into the details in this presentation, but instead point at the reference given below for additional details on the construction of these cones. Until now, we were considering objects moving on a plane. Let us now consider scenarios of objects moving in three-dimensional space. So in this figure, A and B represent two arbitrarily shaped objects moving with velocities VA and VB. Then we can essentially construct planes that cut through both the objects and construct planar sections of the collision cone on each such plane. Subsequently combine these 2D planar cones and obtain a composite 3D cone. So we essentially construct these individual planes that cut through the objects A and B. And on each such plane, we compute the angle psi, which in general will be different from one plane to the next. And we then determine the components of v theta and Vr on each plane, and then use the equations we have seen in the previous slide to get the 3D collision cone. Now, if we look at the computational complexity of this process, the literature commonly approximates objects of irregular shape in 3D using multiple spheres. So if we were to use, say, P spheres for object A and Q spheres for object B, then the computational complexity becomes order of P times order of Q, which represents a quadratic increase. On the other hand, by using a plane which cuts through both A and B, then the computational complexity increases with the number of planes, which essentially is a linear increase. Now, there is a computational cost to calculating psi for these 3D objects. And if A is a point object, then it is easier to calculate psi. But when A and B are both solid 3D objects, then calculating psi becomes harder. Now, if we consider this situation wherein A and B are both quadric objects, and examples of objects formed by combining various quadric objects such as ellipsoids, paraboloids, and 1 and 2 sheeted hyperboloids are shown in the two figures on the left. Now, then there are tools that one can use from projective geometry, and we can adopt those tools to calculate the angle psi. And this can be used to calculate psi even between objects of heterogeneous shapes, which belong to the class of quadric surfaces, such as an engagement between an ellipse and a parabola, or a parabola versus hyperbola, and so on. And this can lead to collision cones wherein the cross-section of the cone is non-convex, as shown in the figure on the bottom. I will not go into the details in this talk, but point to the reference given below for further details. So we have discussed collision cones in 2 dimensions and 3 dimensions. Now let's look at the same in n-dimensional space. Let's start with the figure on the left, which looks at an engagement geometry between 2 point objects moving in n dimensions. Here VA and VB are their respective velocity vectors, each of which have n components. The line joining A and B is referred to as the LOS as before. We can then resolve the relative velocity vector VB minus VA into a component VR, which acts along the LOS, and n minus 1 components v theta 1, v theta 2, and so on, which are mutually orthogonal to each other and also orthogonal to the LOS. Then A is on a collision course with B if the LOS does not rotate in the n-dimensional space and also is shrinking in length. So this is equivalent to the condition v theta 1 equal to v theta 2 equal to ... v theta n minus 1 equal to 0, Vr less than 0 as shown in the boxed equation in red. So using these conditions, we can determine the heading vector of A, which will cause A to lie on a collision course with B. It is then possible to generalize these ideas to collision between point and various quadric surfaces in n dimensions, that is hyperquadric surfaces. And some examples are shown in the right 2 figures on the top row. These show the engagement between a point object and a hyperspheroid. And the rightmost figure shows the engagement between a point object and a non-convex confocal quadric formed by the intersection of a hyperboloid and an ellipsoid. So these collision cones are now heading angles in n-dimensional space. An example illustrating the collision cone in a 4-dimensional space is shown in the figure on the bottom right. For more details, I will just give this reference listed at the bottom of the paper. The collision cone was originally developed for the purpose of collision avoidance. We essentially construct the collision cone from an object A to an object B, which are both moving in either 2 dimensions, 3 dimensions, or n-dimensional space. And if the current velocity vector of A lies inside the collision cone, then this means that A is on a course to collide with B. And this is the scenario shown in the figure on the left. Then, for the purpose of collision avoidance, A essentially needs to apply a suitable lateral acceleration to steer its velocity vector so as to drive it outside the collision cone. And since we have analytical expressions of the collision cone for different object-shaped pairs, we can employ different control methods to compute the lateral acceleration and thereby develop guidance laws based on dynamic inversion, sliding mode, Lyapunov-based, and so on. Now, it is also possible to use such cones for an additional broader class of motion applications. And that is a scenario schematically shown in the right, wherein it would be of interest for us to drive the velocity vector of A into the collision cone by applying a suitable acceleration. So this larger class of motion applications we will touch on in the subsequent slides. Consider the situation when we need a UAV to pass through a moving window. We can construct a 3D velocity cone, which we will refer to as a safe passage cone, which comprises the set of heading angles of the UAV with which it can pass through the window. The figure on the left shows the engagement geometry between a line element and an ellipse. The ellipse here is the largest ellipse that can be constructed to fit inside the window, and the line element is essentially a diagonal on the quadcopter planform. And we make it so that the line element passing through the ellipse is equivalent to the quadcopter passing through the window. Now, by taking the surface of revolution of the ellipse about its major or minor axis, we obtain a spheroid, and we then construct the safe passage cone from the line element to the spheroid, and eventually determine a lateral acceleration that will maneuver the line element through the spheroid, through the ellipse. So an illustrative simulation is shown in the figure on the right, and more details are given in the paper referred to below. There are scenarios wherein UAVs need to move along trajectories that causes an overlap of their sensing or communication footprints. The figure on the left shows a group of UAVs performing an agricultural spraying operation. Assume that the oval region around each UAV represents a spray region of that UAV, and we refer to that as the UAV's footprint. The UAVs need to move along trajectories such that their spray footprints overlap to some desired extent. Too much overlap will cause some regions to be oversprayed, while too little overlap or no overlap can have the opposite effect. So we construct the velocity cone, which for this application we refer to as a rendezvous cone. And this rendezvous cone contains a set of heading angles of a UAV so that its footprint achieves a rendezvous with the footprint of another UAV to some desired extent of overlap. In the scenario shown in the right figure, two UAVs referred to as SUAV1 and SUAV2 need to communicate with each other. The oval regions shown around each of these UAVs represents their respective communication footprints, which are in general non-isotropic. A relay UAV then flies into the path corresponding to an overlap of the communication footprints of itself with that of UAV1 and UAV2, and thereby facilitates communication between UAV1 and SUAV2. In another application, we consider a group of UAVs carrying a net with the objective of intercepting an intruder UAV or a swarm of intruder UAVs. In the figure on the left, the three UAVs are at A1, A2, A3, and the intruder UAV is assumed to be enclosed in the sphere B. So the three UAVs A1, A2, A3 are essentially carrying the corners, the three corners of this triangular net. We then construct the collision cone from any chosen intercept point on the net to the sphere B, and then ensure that the three UAVs A1, A2, and A3 apply coordinated acceleration inputs so that they maneuver the velocity vector of the point X on the net inside the collision cone, while at the same time orienting the net appropriately so that they can intercept the intruder UAV with an appropriate net angle. The figure on the right shows some Monte Carlo simulations of the net carrying UAVs intercepting the intruder UAV from several different initial conditions. It is also possible to use the collision cone framework to achieve interception with pre-specified impact angle constraints. Some representative simulations are shown in these figures. Here we essentially construct the collision cone from a point missile to a circle whose radius is equal to the missile's blast radius, which is centered on the target. And then we achieve, by achieving interception at different points on this circle, we can achieve different impact angles. So these figures here show what I just mentioned. Essentially, the target is performing different kinds of maneuvers, and interception is achieved with different impact angles.